Welcome to my channel and welcome to you, Alexander. You're a guest here at my office today, and we're going to talk about some of your research mainly from your PhD, I guess. Alexander has been here for some years,
Two and a half it's been now.
2.5, and is towards the end of his PhD with
finishing September. So
Sophie Marie Coxpan
Yes.
is your supervisor. You saw her on this channel maybe a year ago or so, but you're doing something a little different than your supervisor, but still within the field of
it's in the same directions, yes.
the general cosmology, you could say, but it's a lot more specific in your case.
We're quite interested in cosmology. You often make this assumption that the universe is very homogeneous and isotropic if you zoom out far enough. So you imagine if you keep zooming out, you will see roughly the same density, roughly the same number of galaxies. And that's how you sort of solve the math, because it's difficult to do it otherwise.
That's basically what we said for 100 years or more. That in order to actually be able to work with the numbers and the theories, well, we assume that everything is homogeneous and isotropic.
Yeah, it's because Einstein's theory of relativity is really hard to solve. So you usually need some symmetry assumptions, some simplifying assumptions to solve it. And in cosmology, is this, if I look from far enough away, stuff looks sort of smoothed out. But then what we care about is, it's not true, right? If you go to small scales, you will have places in the universe where you have a galaxy or a galaxy cluster sitting, and then right next to it, there's nothing. So when you have light coming to us from a galaxy, from anything we observe, it will travel through empty space mostly, sometimes pass by a galaxy. Because Einstein's theory says light gets deflected in such a case, it will then bend a little. And so you get sort of these very crinkled trajectories. And what we care about is, how does that mess up our observations? How does it influence the cosmological model? So that's the big scope.
Because when people are often presenting new results from large-scale structures or even very large-scale structures, the interesting part is always in the lumpiness. That people find some specific objects at certain wavelengths and at certain distances, and these are quite interesting. But it also means that on these scales, the universe is not homogeneous in any way. I mean, you find a lot of interesting objects and lumpiness around, but you're now saying that this is more like the general rule.
The lumpiness is sort of what makes it interesting, right? If you don't have any lumpiness, you don't have us. We are lumpiness. And the same for the galaxies. But we care what the lumpiness does to our observations. So the light, as it travels, how does it get deflected, and so on.
So what are you working on, or what have you been working on these 2.5 years?
So I think two very big projects I did was at a new type of observable that we will be able to measure. We're not doing it yet, but we just built a telescope that will be able to do it. And it's called real-time cosmology. So the idea is to look at a galaxy's redshift or position today, and have a look again in maybe 10, 20 years, and see how has that changed. How has the galaxy slightly drifted across the sky? How has its redshift changed? And these are really cool observables, because they give you insight into the dynamics of the universe, not just a static picture. And we hope to learn a lot from this. We did some investigating how these variables would look in a lumpy universe.
So this work is related to the whole redshift drift and the papers that you made on that. I earlier quoted some of these papers of Alexander and his colleagues on this channel, and the term redshift drift is really the
change in redshift. How is the redshift changing? And
that's also the real-time cosmology.
That's the same thing, right? So real-time cosmology is the overarching category for all of the variables that change. So there was one paper we did on redshift drift. So how does the redshift change over time? And one we did on position drift, is how does a galaxy position change? If you watch it for a while. And these are real-time cosmology observables. And then the individual ones are always called drift. For some reason.
So redshift drift is the change in redshift, and the redshift is the whole moving or expansion of the universe, in a homogeneous isotropic model and so on. It's just
yeah. The idea is that so if you look at a galaxy and it emits light, that light as it travels through the universe gets stretched a bit. So wavelengths get shifted. And we can measure this because there's some atomic frequencies happen at very specific wavelengths. So we can figure out, what would it have been emitted as? And how did we see it? And then that change in wavelength we call the redshift. And it's sort of like exactly like the Doppler effect, just for light. And then you can figure out how fast is stuff moving away from us.
Yeah, so the difference in the color of the light or the wavelength translates into the velocity of the thing and overall moving away from us.
The faster something is moving away from us, the redder it will appear. That's why you call it redshift.
But then you look at the change in this.
In redshift.
So it's really also the acceleration.
It is exactly the acceleration. And it's, I think, what people find quite exciting about this variable, because it will be the first direct measurement of the accelerated expansion of the universe. So we've known for a while now that the universe has to expand in an accelerated manner. So it's not only expanding, but this is getting faster and faster. But we usually do this with indirect measurements, right? So we look at what we call standard candles, where we know how bright they should be.
Like supernovas.
Exactly.
And variable stars.
And by seeing how bright they actually appear, we can figure out how far away they are. And from the distance, we can figure out how fast are they moving away and what should the expansion of the universe be. But if we measure this redshift drift, you can forget about the distances. It's a direct, I subtract these two numbers, I see if the universe is accelerating or not. And I think it's this direct test we haven't had yet. And that would also be a direct confirmation of dark energy. So far, the inference is sort of indirect. And this would really be, if we see a positive drift, the universe is accelerating, and we have dark energy.
So now you said dark energy. I was thinking a little bit about that. So of course, dark energy is something that you might say that we invoke to explain the acceleration of the universe overall. So my question was, could you put any kind of limits on what dark energy is through this type of of observations?
So if you get a number of these data points, you would see how dark energy behaves. And if you manage to measure the redshift drift at different redshifts, so at different evolutionary stages of the universe.
Back in time.
Back in time. Then you could see how did the acceleration change over that time. And that would give you a lot of constraints on how dark energy behaves over time, right? Which would tell you something about what it is.
The change in the distance, the change in velocity is acceleration, but also the change of the acceleration. So you're in the one more derivative.
So I mean, what usually happens is, right, as you look out into the universe, you look into the past, because light takes some time to get to you. And then redshift is a good indication of that. So if you see something with a high redshift, it's far in the past. And now you could sort of imagine measuring the redshift drift for individual galaxies further and further away from us. So then you will see the acceleration as it was at one time, and then a bit more in the past, and a bit more. So you see the change of the acceleration as the universe aged.
But going back to the lumpy universe that is not homogeneous and so on, then looking in that distance may be different from looking at the other distance. That's kind of the definition.
That was roughly what we were interested in, right? So in this homogeneous universe, anywhere in the sky, I mean, that's more the isotropic feature, really. Any direction is exactly equivalent. You would see the same redshift drift or something everywhere in the sky. But now, if you have structure, it might change depending on where you look. And we were interested in, is that going to bias our results?
Exactly.
Also, is the signal sort of changed when it passes through all of these structures on its way to us? And is it changed in a systematic way? That would, of course, be really important, right? Do you see a positive redshift drift just because the light did funky things and the mean is sort of biased, or do you see it because you have this dark energy?
Yeah.
So this was the project we did.
Yeah.
Maybe I can tell about that.
Yeah, please do.
So we set up sort of toy universes in the computer.
Yeah.
You run, I think it's billions of particles or something, and you solve the Einstein field equations and see where they all end up, and then you have sort of a toy universe in the end, and you can send light rays through that toy universe. So really what we do is we put an observer somewhere in the box, and we have them look into the sky. And we do this by sort of, it's a shooting algorithm. So you shoot the light ray, and you figure out how does it get deflected and until it gets to my source. You do the shooting a few times until your light ray hits the source, and then you know exactly how it got deflected and whatever, and you can sort of make mock observations, and you can do it all over the sky. You can do it for many observers in the box. So then you can figure out, on average, do I see what I expect, or does something funky happen?
Does something funky happen then?
No.
Clear answer.
So luckily, the mean seems unbiased. So you take, take many of these redshift drift observations. On average, you see what you would expect in this smoothed out universe. This is really good, right? Because this is the measurement we want to do, and we don't want it to be biased, because that will be tough for our observations. But what we did notice as well was if you happen to look at a galaxy sitting in a galaxy cluster or something, then the peculiar acceleration, so the acceleration caused by infall into that cluster, actually does introduce some large scatter to the redshift drift. So you can imagine you have the mean signal. If you imagine a curve, you'll have the mean is unbiased, but there will be a large scatter around it. And maybe from the scatter, we can actually learn something about gravity in these clusters. So we noticed that scatter signal is quite large as well, and can actually sort of in the close by universe reach the same order of magnitude as the background signal. And that could teach us about the gravitational forces in these clusters.
Gravitational physics, basically.
Really cool, so it's essentially right, because you have F is ma, so the force is proportional to mass times acceleration.
Newton's second law.
Exactly. If you measure the acceleration through this redshift drift in such a cluster, you would be directly constraining the forces in that cluster, which would be a cool test of Einstein's theory of gravity and such things.
So it's really cool that you're kind of tackling a 100-year-old problem that's at the foundation of cosmology and the foundation of physics, and you're doing that now. Is that what you're going to continue to do, or what are your next projects?
So there's one project on the table about actually studying this contribution to the signal from these clusters. So can we learn something about local gravitational physics in these galaxy clusters from this type of signal? I would kind of like to do that, run a simulation and study what happens in these clusters. You need a bit higher resolution. You need to do some other things.
You always need higher resolution. Faster computers.
bigger computers, more computing power. We now did the first iteration of these studies, right? And for the initial test, you always run a small simulation. So you only go that far into the past. So we only constrain things until redshift 0.4, if that tells anyone anything. And one of the things
that's not very far
to
the
run
past.
No, it's not that far. One would be to run a bigger simulation, because some of the actual observations with the telescopes we're building now will be made at redshift 2 to 4, maybe 6. So we would need a bigger computer simulation. So now that we have the proof of concept of we can actually calculate this, we would like to study it in a bigger setting. And
So one trick when you do computer simulations and you want to see how resolution affects, rather than just going for the big shot, sometimes you can try to downscale. So you have one experiment at one size, and then you do half the size, too small, in order to what you want, but just to see the resolution.
That's what we usually do to test if the code is working well.
Exactly.
Right? So
exactly.
so even for the paper we did a small universe first.
Yeah.
But then we did a universe that was also small but had half the particles, and we see do the results hold up in this sort of worse model, right? If you have less particles, then you have it's sort of like a coarse-grained image. So it's sort of if you set the video quality somewhat lower, then you can get an idea of is it still the same.
Exactly.
And then if the results agree, then you can say, okay, we know this is good enough, and we can publish the results from the higher resolution. And then of course, once you know, oh, my code is working, because you want that confirmation. You don't want to run a big simulation for a week without knowing this. Then you say, okay, and now let's make a big universe and see what's going on. So this was on the agenda.
Going back to this universe, which is really big, considering just one particle, namely you, what are you going to do in the future? What are your plans in the long run? What are your dreams? You just need a bigger computer and then everything is solved, or?
I don't think that's the the ultimate solution. I always like to work both with computers, but also do quite a lot of theory calculations. So it's a mix of both. I mean, I'll finish my PhD soon, so I'm looking to stay at some university and do a postdoc.
That's kind of like a suggestion. If there's anybody out there at a university that has an open position for a postdoc, one is right here.
Yes. So starting September, I'll be looking for. I'm already looking. For another position. I'd love to stay in academia and continue.
This extremely important work. I mean, this is the foundations of parts of physics that you're working on. So I think it's really, really important work that you're doing, and I hope to see more of it. I guess that you are going to publish something more, and perhaps you'll see it here on this channel. So with that, I would like to thank you for coming today.
Thank you.
So it was a great pleasure, and I hope you enjoyed it. See you.
See you.